welcome you for the ACT sponsored FDP on emerging technologies in wireless communication. So I'm requesting to Suharika to introduce the today's speaker to audience.
Okay, so I want to share the slides now, right? Yeah.
Dr. M. Surinder is currently working as an assistant professor in Electronics and Communication Engineering Department at NIT Puducherry since July 2018. He has completed his BE Electronics and Communication Engineering in Tyagaraja College of Engineering, Madurai in 2010 and ME Wireless Technology in the same institute in 2012. He has done his PhD in National Institute of Technology, Tiruchirappalli in 2017, Department of Electronics and Communication Engineering. Under the guidance of Dr. P. Chidambarathan, after his PhD, he worked in Sangya Labs Private Limited, a software-defined radio-based company, as a senior member technical staff for 1 year. His current areas of research include 5G and beyond wireless communication, physical layer signal processing, massive MIMO, ultra-low latency communication, and multiple access techniques. He had published his research papers in many reputed SCI indexed journals. So far, 3 PhD research scholars have completed PhDs under his guidance. He was one of the co-principal investigator of a project entitled Receiver designed for low latency 5G wireless communication, funded by Sri Lankan Technological University in collaboration with Professor Dr. Naresh. Thank you.
Sir, can you share that screen, sir? Now you can present, sir. Hello, sir.
Sorry,
Yeah, I hope I am audible and my screen is visible.
Sir, yes, sir, you are audible, sir. Yes, sir. Sir, we can go ahead, sir. Hello, good afternoon, sir.
My
Am I
screen
audible?
visible? Just now.
Hello. Sir, you are
Hello.
audible. Go ahead, sir.
Is my screen visible? Yeah, I am audible. Okay, but is my screen visible?
Yes, sir, you are audible, sir.
Okay.
Hello.
Okay. Yeah, I'm trying to make my screen visible. Yeah, due to poor internet connection, we are facing
Okay,
some
sir.
issues. In just a few minutes.
Okay, sir.
Dr. Srinivas, can I start? Is my screen visible? Our internet connection is back.
No, sir, no, sir. Your screen is not visible.
Please share.
Okay.
Please, sir. Please share that.
I started sharing. A minute. I'll share again. Just you can see. Is it visible now?
No, no, sir. So far, no. Screening not actually. Sir.
Left
Kill.
yes, join and share it.
Dr. Srinivas, I don't know why my screen is not showing up. Even I'm checking with other phone. Um, is there any other thing, any other
Sir,
permission
no, no.
pending
Wait.
from your side, or
From our end, there is no issue, sir. Actually, you can share
okay?
it.
See, I'm stopped sharing now. Actually, my screen is shared right now. If
Can I share? Actually, for us also, it is showing the sharing option. So, can you rejoin, sir?
yeah, I will rejoin then. I will rejoin.
இருக்கு சார் நெட் இருக்கு.
See the screen. Okay.
Sir,
Yeah,
now
I hope my screen
yes,
is visible now, right?
Yes, sir,
Yeah,
yes,
I'm
sir.
also checking here. I restarted, so yeah.
Sir, can you maximize?
Yeah, I'll.
Yes, sir. Yes, sir. Now
Is it okay?
Yes, sir. Yes, sir.
Yeah, I'll proceed now. Yeah.
Yes.
Okay. So thanks to Dr. Srinivas for inviting me for this FDP. I hope I have went through the brochure, and it seems interesting that many physical layer concepts are a part of this FDP, and I have went through other topics also, and as much as possible, with the minimum overlap, I will try to deliver some new parts of the same topic. Maybe some might have discussed about RSMA introduction. We will see a bit more about RSMA on that, because RSMA is the most important part of multiple access techniques right now, and how it is superior than many other existing techniques, multiple access techniques like SDMA and NOMA particularly. So we will see that in this session of discussion. And if anyone have any doubts, you please unmute yourself and you can ask your doubts at any time. So as a part of this, let's start this. Yeah. So I think the motivation for any communication engineer um, might be, this might be a kind of a repetitive slide. This slide you can see anywhere if you go. This is the motivation basically we have behind any communication, particularly when we talk about 5G, 6G, and beyond. We always say that we need a better throughput. Better throughput means a better data rate. We require a better data rate within a square kilometer. That means within a coverage region, we require a better throughput. So that better throughput can be achieved by tuning any of these three parameters. One is cell density, another one is available spectrum, and another one is spectral efficiency. So now let's talk about the cell density. Cell density is basically how many number of towers do we have? How many number of base stations had we installed to make the coverage? So in that way, we have the cell density thing, and this cell density, if we are keep increasing the number of cells in a coverage area, we can make sure more users are covered, more number of users are covered, and everyone are served with a better data rate. So this is one part. But is this practically, to an extent it is possible, but definitely not for a not every time it is not possible. But with when it comes to 5G, 6G, as we move towards the higher order frequency, the penetration will be very lesser for higher frequency. So obviously there is going to be a lot of base stations coming up in future, and the base station will not be as complex structure as now we have. Actually, even now you can see the 5G base stations. It's not like kind of Eiffel Tower thing. It's just a rod, huge shallow pipe that has been mounted in the ground, and at the top of it you can see a lot of antennas right now. So it is no more space constraints, will be much more lesser compared to the previous 3G, 4G base station towers. So that is one thing. And uh, next is the available spectrum. Generally, we know that spectrum has been auctioned recently by Indian government, based on the guidelines of TROI, regulatory TROI is a regulatory body. They will decide what is a base price that can be given for a particular bandwidth. You can see that 45% of the bandwidth is purchased by is actually taken in auction by Geo, and Airtel is having a fair share. Around 40% they do have it, and around 5% is taken by Vodafone Idea and BSNL, and one more player also coming in, Adani. What I hear is Adani is also a part of this auction, and he has also auctioned some important bands at lower frequencies. Maybe he may have some applications in his industries, and for to increase the productivity, everything they may require this spectrum. We have to wait and see what they are up to. And available spectrum is increasing. The available spectrum is a natural possibility to increase the throughput. Yes, but the thing is, it's not. It's an expensive process, because 1 megahertz has been sold around 450 crores, around 4 gigahertz actually. When it comes to 700 megahertz, around, let's say the central frequency is around 700 megahertz or less than that. The spectrum is more than 1,000 crores, 1,000 or 4,000. I vaguely remember the values. The 1 megahertz is around 4,000 crores. This is because of the fact that the low frequency can penetrate very well. So you don't want to install much of base stations there. So low frequencies, and also the bandwidth is very less at low frequency. But when we move towards a higher order bandwidth, higher order frequency, we get proportionate bandwidth also. But it cannot penetrate very easily. You need a solid network structure to get the complete coverage. So the price difference will be there with respect to the central frequency, and whatever it is, the price of available spectrum, to increase the available spectrum, is so high, so the throughput will be so that we can get the throughput. But touching there is not a technical. It's more of a money oriented thing. So the third one is the spectral efficiency. That means within a hertz, how many bits per second can be sent. That is given by the spectral efficiency, and this can be actually manipulated by using various techniques, like as we are talking earlier, multiple access techniques like NOMA and RSMA, and this spectral efficiency is going to be the research part. It's the major research part will come into this contribution towards this research, that spectral efficiency, so that we can get a better throughput there. And these are all the things to be reviewed before discussing RSMA. Of course, many slides you may feel repetitive. I will run through those slides. I will discuss some important mathematical equations for RSMA, because those mathematical equations can help you understand RSMA in a better way. Okay, now orthogonal multiple access. So orthogonal multiple access, of course, we know TDMA, FDMA, CDMA. This TDMA, you can see the time is divided among each user, and each user will be occupying the complete frequency. And in FDMA, the exact opposite. The frequency based on frequency slot is completely, for a complete amount of time, is allotted to one person and one user in the sense. And in CDMA, multiple users are using the same band, the same frequency, and the same time, but they are separated using a different code. So that's why CDMA is also a very effective technique, but not in India, because maybe because of the more number of users. And later on, for 4G and other technologies, we have OFDMA, that is orthogonal frequency division multiple access. This has multiple users using different frequency slot and different time slot, and you can see the spacing between one user and another user, that is one frequency band and another frequency band, those are all called the subcarriers here. They are very tight because the subcarriers are orthogonal to each other. That's why we call that as an orthogonal frequency division multiplexers. So here each and every color corresponds to one user. The color code is basically given to differentiate the users. Here you can see in OFDM, a user is not only given a different frequency, but with respect to time also that frequency is getting changed. So with OFDM, there is some concept called the carrier aggregation and other things. So that plays an important role in switching carriers time to time. So that makes the bandwidth always occupied with the user's information. That's why we are getting a better bandwidth or better data rate in 4G or 5G. So this is one of the basic multiple access technique. You can see space division multiplexers. That means we have multiple number of antennas at the transmitter. And in this scenario, we have only one antenna at the receiver here. So the thing about SDMA is that, and this is to be noted that this figure is basically taken from the paper that is given below, is no more efficient in multi-antenna networks. So that is a question to be answered in this actual discussion, so that we get to know what is RSMA is clearly. And the space division multiplexers, if you see, it will serve multiple users at the same time. Of course, NOMA also does that. RSMA also do that. SDMA also do that. And how that is possible, first of all. So this is a basic SDMA technique, and you can see each user are given with a separate beam here. So this means that even if there is an interference due to, let's consider user 1, even if there is a interference due to user 2 signal in user 1, it completely treats that as a noise. I mean, the receiver will completely treats that as a noise, and this SDMA requires channel state information at the transmitter also. So these are all some notable things in SDMA. And remember, SDMA is a basic technique that can also serve multiple number of users. And why this RSMA stands out of SDMA, we need to understand. For understanding that, we are first explaining the SDMA, how the transmit signal is and how it is received in the receiver. Here you can see that the transmit signal is composed of, I hope. Here you can see that the transmit signal is composed of all the users information, S1, S2 till Sk. Totally capital K number of users are there, and P1, P2, P3 are beamforming vectors. We can say that is we can say that as a beamformers, and we have the received signal at user K, and we have the received signal at user K. Once it is received at while receiving, the composite signal X, which consists of K user signal, is transmitted through the channel HK towards user K, and you can see this HK is multiplied with all the P1, P2, P3 till PK, and only the user K, the kth information stands out, and others are considered as noise in SDMA. So the logic behind that is, whatever since it is since the channel coefficients doesn't match with the beamformers, let's say when I is not equal to K, whatever the channel coefficient, whatever the beamformers apart from K, every others will be considered as an interference, and they will be cancelled out. Actually, they will be treated as noise. They will be considered as noise. That's why we have in sum rate, you can see sum rate is sum of RK. RK means user kth users rate, small kth users rate. So K will be from varying from 1 to capital K, and if you sum each and every user's individual rate, you can get the sum rate. And this RK is actually given by, based on Shannon's capacity theorem. You can see that log to the base 2 of 1 plus 1 plus SINR actually. Here it is considered as SNR because interference is also considered as noise. So this particular part, the second part of this particular equation is taken down in the denominator of this particular equation plus sigma k square. Sigma k square corresponds to the variance of the noise nk, variance of the noise nk. That's why we have the rate like this. And it is to be noted that SDMA treats completely the SDMA, the way SDMA treats the interference is uh, completely noise. Interference is completely noise. There is no such thing called interference. Like that, it will treat and it will complete the process. The problem with this SDMA is that we need exact CSIT. If the CSIT is not appropriate, if the CSIT is very poor, let's say, or not even very poor, even if there is a mild change in CSIT, we would have estimated something, there might be some error in our estimation, so we may not able to get the proper CSIT at the receiver. So at that time, at the transmitter and or the receiver, somewhere if there is a mismatch between the actual CSIT and the estimated CSIT, then this SDMA performance cannot consider this interference as noise. So there will be a performance degradation due to the interference, due to improper channel estimation. So that's why SDMA is not so reliable so far. SDMA is not considered very seriously like superimposing coding, like superimposed coding like NOMA so far. And later on, there comes NOMA. You can see NOMA would have been already discussed. I'll just run through a few slides. This is a very famous diagram you could have seen anywhere. Whoever discussing NOMA, they will be using this diagram. So there are two users, one is far user and one is near user. So near user has to do two things. One is he has to detect the other user's information, that is a far user's information, and he has to recover his own symbol from SIC, that is successive interference cancellation. Through SIC, he can recover his own signal. Whereas user one, that is a far user, in this case, far user, they can directly take out their take out the information from that. And if there are more than two users are there, let's say if there are more than two users are there, let's say there are four users, the four users has to be sorted based on their channel strength or distances. Basically, distance will determine the channel strength or the way. Some people would be sitting inside the room and they want to access the phone. So for them also, there is a possibility that the channel coefficient, channel gain would not be that better. Okay, based on the channel gain, the users are sorted. Voice. Hello. Ah, yeah.
Sir, you are audible now, sir.
Yeah. In between there was some problem. Yeah. So just a minute. Ah. Here, if there are multiple users, I was saying, I don't know when the audio got disconnected. When there are multiple users, here only two users are there. So one user has to do this SIC. Whereas when there are four users are there, or multiple users, more than two users are there, they have to do execute one of the user has to execute the SIC for 3 times, and another user has to execute the SIC for 2 times, and another user for 1 time, and another user goes without any additional complexity of doing SIC. That is a foremost user. He don't have any problem. He will just decode his own message and he will leave. But the other users, and remember, our mobile phones are designed to communicate, and it is not supposed to do a lot of signal processing task. So as much as possible, we should take the load of the users, actual users. Better to have more load at the base station, because base stations are powered with a lot of power sources. High energy generators are used there, so it can handle any amount of signal processing task. So, but a user will have just a small device with him. So that small device, if it's keep executing some decoding part and other things, if it is keep wasting its power, then battery life will be very weak. So these are all some disadvantages if we are increasing the whatever we are trying to do. Try to do at the base station. When it is downlink, try to do it as a base station level. Even at the uplink also, as much as possible, offload things from the user. So that is the main idea. And NOMA is having an issue of having multiple SIC layers when you are going for more than 2 users. So these equation or very familiar equation. You can see this S is a transmitted signal, that is a superimposed signal. S1 and S2 are the symbols that corresponds to user 1 and 2. P1 and P2 are the power allocation factors, and rho S is the SNR that has been used. And this rho S is composed of this total transmit power PS, and the received signal at the ith user is actually given by YA is equal to HI into S plus NI, because HI is the HI corresponds to the channel towards the ith user, between the base station and the ith user. And for I will run through this derivation. This is a very small derivation only. So the user one, that is a for user in this case, the user one, first he will be obtaining his message directly, because the for user generally, let's say the for user is given a power coefficient of 75%, and 25% is given to the near user data. And when the composite signal, that is the superimposed signal, reaches the for user, he will be having a very minimal level of near user data. So majorly his signal will be composed of his own data. So directly he can consider the user 2's data as a interference, and he can decode his own messages. So that is for user NOMA. That is for user in the NOMA. And the achievable rate, as usual, it is calculated by here you can see the numerator part corresponds to the signal power part, and the denominator part corresponds to the corresponds to the interference part, interference due to user 2's information. And we have this one because the noise is normalized to 1 here. And the achievable rate is given by log to the base 2 of 1 plus SINR. So the achievable rate of user 1 is actually given by log to the base 2 of 1 plus SINR. Now coming to the user 2, user 2 will actually do something called SIC. As user 2 is very nearby, his signal is majorly consisting of the for user signal, because for user signal is given 75% of the power there. So what he does is, the near user will first decode the other user's information, that is the user 1's information, for user's information, and from that for user information, using that for user information, he will cancel that for user information from the received signal, so that his own signal will be reappearing. I mean, his own signal will be appearing without any interference, because remember, we are doing SIC, successive interference cancellation. So once the interference is cancelled, only the remaining signal part, that is his own signal, will be there. So his own signal is there. That's why we no more have a SINR, we have a SNR, signal to noise ratio. It's not SINR. That's why remember this is divided by 1, because noise is normalized to 1. Noise power or variance is normalized to 1. And we have the achievable rate for user 2 given here, and the sum rate is actually given by the sum of two achievable rates. This is the for user achievable rate, and this is the near user achievable rate. And at higher SNR, you can see some approximations are actually done, and at higher SNR, we are obtaining an equation like this. Now, let's compare this OMA with NOMA. So, OMA, what the OMA does is, let's say, here we are using half of the bandwidth or half of the time for user 1, and half of the time the complete bandwidth is used for user 2. So that's why we have a sum rate given like this. And here, when we try to approximate, let's say the user 2 is near user, remember, user 2 is a near user. So the user 2 will have a strongest of channel gain when compared to the user 1. So this H2 square, this modulus of H2 square will be very, very greater. There is a gain of near user will be very, very greater than the gain of user 1. So we are approximating the sum rate of OMA to here. And now let's compare the sum rate of NOMA. That is, we derived the previous section. We have derived this. When we compare these two, obviously NOMA is having a better sum rate when compared to OMA. So here you can see there is a half in OMA, but here it is 1. So that itself is more sufficient because that is 2 times better than that. And within this log 2 also, we have this 1 by P2, that is a power allocation coefficient, which is always less than 1. So when 1 by less than 1 number is there, so inside the log also, it is very favorable to NOMA. So this is why NOMA is claimed to be better than OMA till RSMA comes in. So now let's go into this is a safe way of NOMA, how NOMA is explained so far, because NOMA is shown it is having more merits because it uses the same time and frequency slot. NOMA uses same time and frequency slot for multiple users. That's what they used to claim. But the issue with NOMA is, the real issue with NOMA is, nowadays most of the systems, whatever we have, are having multiple antennas. Let's say a base station. Base station, obviously, it has a space there. It has a required space there. So it has multiple antennas in it. Of course, our mobile right now it can accommodate only one antenna. So our mobile may not have multiple antennas as we think. But a base station can have multiple antennas. Now, the real question we need to answer is how the NOMA performs when it is MISO NOMA. So far, we have seen only SISO NOMA. That means we assumed that our base station is equipped with only one antenna, but in the practical scenarios, it is having multiple antennas. Just 1 minute. So, yeah, any doubts so far? Because we are going to start on MISO NOMA. Yeah, if there are no doubts, I will carry on. Yeah. 1 minute.
Sir, you can continue.
Yeah. I have to show some other slide now. Yeah. Here is. I hope you can see my screen. Okay. So this is about MISO NOMA. You can see this is MISO NOMA. What does that mean? Multiple input, single output NOMA. That means we have multiple number of antennas at the transmitter and single antenna at the receiver. And single antennas, that is each user. Here also a two user scenario. 2 users are having a single antennas each. So here, let's say, I have a composite signal. that we generally have P1 S1 plus P2 S2, and this S1 and S2 are obviously the information that corresponds to user 1 and user 2, and this P1 and P2 are small p1 and small p2. Remember, p1 and p2 are m cross 1 precoders. Why I am saying m cross 1 precoders is that because m is the number of transmit antennas. So remember, we are not having one antenna here, so we are having multiple antennas. So this p1 and p2 are no more a scalar quantity, that is 1 cross 1 quantity. It is a array. Okay, so this p1 and p2 is a vector now, m cross 1 vector. Now this p1 and p2 are actually defined by capital P1 plus capital P2, which is less than or equal to capital P. This P1 and P2 are actually the powers. This capital PK is actually given by small pk norm of small pk square. So we have to ensure that it is the norm of P1, norm of the precoding vectors, the norm of precoding vectors should sum up to maximum to capital P. That's all. That is the maximum power we can have. Here this k is actually equal to 1, 2. So these are all the some basic things with respect to the system model we are considering here. And when we calculate the rate, of the first user, okay, so rate of the first user, this n corresponds to NOMA. I'm taking the notations with respect to is NOMA efficient in multi-antenna scenario. That paper, from that paper only I am taking the notations. So if you want more clarity, you just go through that paper. That is better. That paper gives a very strong comparison of NOMA with the RSMA. So this R1 of n is actually given by log to the base 2 of 1 plus H1 Hermitian P1. Okay, P1 square. This is because my X signal is going to be transmitted through H1 and H2. These two channels it will be going to be transmitted. So when it reaches user 1, it will be reaching there through H1, and the signal power that corresponds to user 1 is H1 Hermitian small p1. So this modular square, we have the rate of first user now, and the rate of second user. This rate is generally how we derived in the last slides, as we are showing. When I'm trying to explain about SISO, NOMA versus OMA case, we have this the similar derivation is applied here, but the only difference is these are all vectors. They are all no more a single value. These are all vectors. So R2, this is for user 2. The other, for other one, we have minimum of, what is the minimum among log of 1 plus A, comma, log of 1 plus B. I'll tell what is this A and B are. This A is actually equal to H1 Hermitian P1 the whole square divided by 1 plus H1 Hermitian P1 the whole square. This is P2, sorry. This is P2, and we have B is equal to H2 Hermitian P2 the whole square divided by, remember this is for symbol 1 S1, this is for symbol 2 S2, this is for S1 and this is for S2. So I'll explain what is what. So this is 1 plus H2 Hermitian P1 square. This is P1 square. So here, what is A and what is B is that A is user 1. Let me write that too. A is user 1 decoding user 2. User 2 signal. Okay. User 1 decoding user 2 signal. That means the signal is reaching user 1. Remember. So the H1 is there and it is decoding user 2. User 2 signal. User 2 signal is having a power pre-coded matrix of P2. That's why we have the P2 in the numerator. So user 1 decoding user 2 signal and treats its own signal as noise, right? Because user 1 is treating its own signal. This pre-coded matrix corresponds to its own signal, so it treats its own signal as noise. That's why noise or interference, we can say it is interference. So in that way we can write this here. P is literally the same thing, but user 2 decoding, this is user 2 decoding user 2 signal directly, considering user 1 signal as noise or interference. So I hope this must be convincing. Here this minimum is taken into account. This we are having considering minimum. Remember, we can take any of them randomly, but why we are considering minimum among these two is that because both the user 1 and user 2 should be able to decode the user 2's data. Okay, so at least minimum among that rate is so considered. That's why a minimum is taken, and basically this sum rate is less than or equal to. So based on some assumptions, we are assuming that this gets qualified, 1 plus a gets qualified. So my sum rate is actually equal to log to the base 2 of 1 plus h1 Hermitian small p2 square divided by 1 plus h1 Hermitian p1 square plus log to the base 2 of whatever we have for S1, we need to write that. This corresponds to S1's, this corresponds to rate R1, this corresponds to rate, okay, this corresponds to rate R2, okay. So this is the overall sum rate we obtained for my sonoma, and we can do some approximations such that it will be even more clear. So I can write the same equation. We can use this log of a divided by b is equal to log of a minus log of b. Using that logic, we can write this equation as log to the base 2 of 1 plus h1 Hermitian p1 the whole square plus h1 Hermitian p2 the whole square. So I mean, we are approximating the complete, let's say this is equation A. We are approximating this equation A like this. Okay, not approximating. Actually, mathematically, we can write this, because when we take the denominator to here, then we have in the denominator 1 plus h1 Hermitian p1. This 1 plus h1 Hermitian p1 is also here in the numerator. So we can cancel the denominator and the numerator here, so that we are remained with the 1 plus h1 Hermitian p1 square plus h1 Hermitian p2 square. Okay, so this is how we have obtained the equation. Now let's say the decoding order is, user 2 followed by user 1, that means my P1 is actually considered as square root of P1 H1 divided by norm of H1, and my small p2, let's assume that this is what I have considered, H1 divided by norm of H1. When we supply these two H1 and H2 in this equation above, then we obtain Rs is less than or equal to log to the base 2 of 1 plus norm of H1 square capital P. Okay, why we are putting capital P is that because it involves square root of P1 and square root of P2. So we can, this capital P1 and capital P2 is squared and added up so that we can obtain this capital P. Okay, so this is the sum rate we have achieved for NOMA. This is the sum rate we have achieved for NOMA. Similarly, if the if the decoding order is user 1 followed by user 2, then it will be H2 square P. That's all. So that is the difference. And we can say that the sum rate of NOMA, to summarize, if the decoding order is different, then this is H2 square. So we can summarize this as log to the base 2 of 1 plus maximum among norm of H1 square, comma, norm of H2 square. Take whichever is maximum, you just take that and you can calculate what is the sum rate is. Okay, so that we have this almost the same equation we have here. Okay, so this is for NOMA, and this is literally same like our OMA scheme. Here this is more similar to same as OMA. The sum rate is same as OMA. OMA when serving strongest of two users. When serving strongest of two users. Okay, this corresponds to, remember, this corresponds to NOMA. This corresponds to NOMA. For OMA also, we literally have the same equation, and by serving the strongest user always. See, sum rate is achievable rate of user 1 plus user 2. So if a user is having a strong channel, then we can send more amount of data to him. I mean, a more data rate can be achieved, achievable rate can be had by the strongest user, which literally contributes to the sum rate. Okay, but when you talk about the fairness, of course there is a complete misjudgment there. Okay, so fairness, the justice is we need to have the better sum rate. Not only that, we want to ensure there is a rate fairness is also between one user and another user. Okay, it should not be like rich getting very richer and poor getting very poor. No, not like that. Okay, we need to be very much generous to everyone, like that. Okay, so now if you see the OMA's rate, we have already derived, not derived, it's default given. Okay, so 1 plus norm of H1 square capital P plus half times log to the base 2 of 1 plus H2 square capital P. Okay, so this is for OMA. You can compare these two equations. Basically, you can see almost a similar rate. Okay, in fact, at some cases we can say they are the same rate we are getting for NOMA and OMA. But when we have conventionally discussed this OMA and NOMA, it is claimed that NOMA is having, of course, that is true. For SISO scenario, NOMA is having a better performance than OMA. But when it comes to MISO scenario, OMA and NOMA is almost having the same sum rate. Okay, so this is the main issue with NOMA. Now let's compare with another technique which is existing for so long. This is my multi-user linear precoding, that is SDMA. Okay, space division multiple access. Here this is another multiple access technique, and here you can see there is no SIC. Here this is MISO NOMA, so one user is doing SIC and another user is not doing SIC. You can see that, and here none of them are doing SIC. Okay, they just decode their own data, that's all. Okay, for that, how they are forming this transmit uh, composite signal is that x is equal to the same idea, p1 s1 plus p2 s2. Okay, so this pk is actually equal to square root of not p1, it is capital P, that's all, because there is no power factor segregation. 75% power to user 1, 25% power to user 2, no, nothing like that. So we have the total power P that is uh, given to both the users. So but they are multiplied with the beam forming vector normalized with the norm of HK. Okay, so this PK corresponds to HK divided by norm of HK multiplied by square root of their power. Okay, so as per this zero forcing beam forming, this is actually zero forcing beam forming technique. Okay, they call it ZFBF in some papers. Okay, zero forcing beam formers. When we are using that, then we can say that H1 Hermitian P2, small p2 is equal to 0, or we can say H2 Hermitian P1, small p1 is actually equal to 0. Both are actually equal to 0. Okay, so when I multiply P1 with H1, it will not be 0. But when I multiply P1 with H2 or any other H, then it will be 0. Then only this SDMA is working properly. Okay, so this is the property of zero forcing beamformer, and while receiving y1 is actually equal to h1 Hermitian p1 s1 plus p2 s2 plus the noise in 1. Okay, so we have when I expand this Hermitian p1 s1 plus h1 Hermitian p2 s2 plus noise, this will obviously go to 0 because of ZFBF, zero forcing beamformer. So we are remained only with the H1 Hermitian P1 S1 plus N1. In that we can calculate the rate R1 as log to the base 2 of 1 plus now magnitude of H1 Hermitian P1 square. Okay, so when we put this when we substitute this P1 from here, when we substitute this here, or we can use a different pen. When we use this here, when we substitute the P1 from here, we can have R1 is equal to log to the base 2 of 1 plus capital P into norm of H1 square. Okay, so or I can approximately write this as log to the base 2 of P. Okay, so now my RS, that is the sum rate, this is achievable rate. Remember, this is achievable rate, not sum rate. So my achievable rate, sorry, not achievable rate, not sum rate. So my sum rate is actually equal to R1 plus R2, R1 plus R2. So we have 2 times of log to the base p, log to the base of 2 of p. Now you can check the two equations. One is the equation we obtained here, and the other one we have derived earlier, that is RSMA. This is that equation. Okay, this also I will come approximately like this is log to the power base of p. But when I use SDMA, remember when I use SDMA, I'm having we are having a two factor in the front. So my RS of this is my SDMA, remember. Okay, my RS of NOMA is less than that of RS of, that is the sum rate of SDMA. That means we don't want to consider NOMA as better than SDMA, but when it comes to SISO, definitely NOMA has a edge over every other techniques. But when it comes to multiple antenna techniques, definitely NOMA is not going to perform as we think, not going to perform proportionately. One may think like when you are having a one antenna there, we have one performance. When we have two antennas, the performance is doubled. But that is not the case with respect to NOMA. So here, as the number of antennas increases, there are much better techniques are available to take it up. So that is actually this SDMA is having a better edge when it comes to the multiple number of antennas. But the real issue is when it has a poor or imperfect CSI at the transmitter, then it is a problem. Okay, so this is one thing we need to conclude before going into RSMA. And share my PPT again. Here. So we have MISO NOMA. Here you can see the exact same derivation of MISO NOMA, whatever I have derived earlier. And now here comes RSMA. So what this RSMA is capable of? Let me come to this block diagram again, system model diagram again. Before that, I will tell what is this, how this RSMA is designed. So you can compare these three techniques, that is the SDMA, NOMA, and RSMA. It is differentiated by the way it treats the interference. Okay? By the way it treats the interference, it's more like in a cold climate, when there is a fire, we need to have a fire there because the chillness in the atmosphere will actually kill you. But for that you cannot fall into the fire, okay, or you cannot go away from the fire. You need to be in a distance such that that fire has to save us from the very cold temperature, negative temperature in the outside. Okay, the same way we need to treat the interference. Okay, interference should not be treated fully. That means you can't go and fall into the fire, or interference cannot be ignored completely. I mean, one thing is ignoring, or one thing is considering completely. Okay, I hope you can correlate between these two examples actually. Okay, so this SDMA treats this interference completely as noise. That means you are completely moving away from the fire. Whereas this NOMA is treating this interference, I mean, it's decoding the interference completely. In SIC, when it is doing SIC, the interference signal is completely decoded and then it is subtracted actually. So these are the two things we do with respect to SDMA and NOMA respectively. So what this RSMA has came up with is that it is forming a bridge between SDMA and NOMA. Okay, you can see this RSMA is the bridge. You can see this RSMA is a bridge that is formed between SDMA and NOMA. Okay, so this bridge, how we can say it is a bridge between RSMA and SDMA and NOMA is that the way it treats the interference. Now, what the RSMA will do is it will partially decode the interference and it will partially consider the remaining half. Half of the interference it will decode, and half of the interference it will consider as noise. But in SDMA, the interference is completely considered as noise. In NOMA, the interference is completely decoded. Okay, so these two are not good for I mean, in a way, we are having many disadvantages because of it, because we are spending a lot of computational complexity towards that for no use rather. Okay, so when it comes to multi antenna scenario, we have CSIT in the transmitter. Now in RSMA, what it does is, so here you can see a table as given. You can say see a table is given how the interference is treated in all the three techniques. In SDMA, the interference is treated as weak. Why it is weak is that because we treat the interference completely as noise. Whereas in NOMA, we treat the interference very strongly. That means the interference is completely decoded there. Whereas for RSMA, it is treated as weak, it is treated in a medium way, it is treated as strong also. So all three, in all three ways, we are treating this interference. We have the compatibility, we have the feasibility of changing the way we treat the interference, and I will tell you how it is done. So, and remember, this last statements actually suffice. RSMA partially decodes interference and partially treats interference as noise. Okay, so this diagram will make sense once we get to know how RSMA works. So now
Sir,
getting back to
sir,
yes,
sir,
yes,
hello.
yes.
Sir, can we take break, sir? 10 to 15 minutes.
Yeah, sure.
Yeah.
Yeah, sure. Okay.
Yes, sir. After 10 to 15 minutes, again we will rejoin, sir.
Yeah, okay. You call me, I will join again. Huh?
Yes, sir. Yes, sir. As well, I will call, sir.
Okay. Thank you.